Okay, so we're looking at complex numbers. And so complex numbers are basically encompass the real numbers. So the real numbers are a subset of a complex number. And so complex numbers can be written in the form a plus bi. So little a plus little bi, where we say a is the real part of the complex number and b is the imaginary part. Of the complex number. I is equal to the square root of -1. And so if we're dealing with radicals and simplifying them and we have a square root of a negative, we can rewrite it as I. So for example, if we had the square root, let's say, of -96. Well, there's a rule that we can break this up if it's multiplication as the square root of its multiple. So square root of -1 I know is I, and I have root 96. I need to make sure that there's no factor of 96 that is a perfect square. If so, we want to simplify it. And so I'm not sure if it does or not. So I can start breaking it down using prime factors. And so what multiplies to give me, sorry, I don't know why I did 96. Okay, so I know 2 is even, so 2 goes in there. So 2 goes in there 4 times 16, so that would be 48 times. So I can see that this is a perfect square, is going to be in here. I know that this is 2 times 24, which is 2 times 12, 3 times 4. Actually, 4 is not a perfect square, but I know. I mean, 4 is a perfect square, but it's not prime. And 2 times 2. So I'm looking at a number that occurs an even number of times because I'm looking at the square root. So this is 2 occurs 1, 2, 3, 4, 5 times. So if I look at 2 to the 4th times 2 times what else is left? 3. That should give me 96. 2 to the 4th, 2, 4, 8, 16 times 6. Is another way to rewrite the square root of 96. So we would have I times the square root of 16 times the square root of 6. Square root of 16 is 4. So this is 4 times I, 4I root 6. Okay, so just kind of a review really quickly of simplifying some square roots where what the radicand may have a factor that is a perfect square. Be careful when they ask you what the real and the imaginary part is. So if I had 2 minus 3i, a lot of times students want to attach the I when they're stating what the imaginary part is, but you don't. So the real part of this complex number is equal to 2, and the imaginary part is equal to the number in front of the I, which is, and carry the sign. So that would be -3. If I just had, let's say, 7i, and they asked you for the real part here, notice that there's no real number in here. I can think of this as 0 plus 7i. So the real part would be 0. Imaginary part is 7. I was saying that the real numbers are a subset of the complex number because think of it this way. If I'm looking at just the real number 5, the real part is 5 and the imaginary part is 0. Okay, so when we're dealing with complex numbers, we're pretty much dealing with them similar to like when we're dealing with terms like terms. When we're adding complex numbers, you're adding your real parts together and you're adding your imaginary parts together. When we're multiplying complex numbers, we need to just be aware of what I squared is and that, or a multiple of I in there. So let's just kind of review that. So by definition again, I is equal to the square root of -1. So technically, if I square both sides of these equations, then I could say then that I squared, well, squaring the square root, that cancels it, just leaves us with -1. So we might have to raise I to a higher power. And so there's actually a pattern here that we'll notice. And so let's cube this. So the cubed, I cubed, that's the same thing as I squared times I, if we want to rewrite it. I squared, as from above, we know is -1 times this I. So this is -I. I to the 4th, well, we can break it down to values that we know. Well, we know I squared times I squared is I to the 4th. By the rule, same base multiplication, you add your exponents. Well, I squared is -1 times I squared, which is -1, which is +1. So I to the 5th, this is equal to, a couple ways we can break it down. We know what I to the 4th is from above, times I. I to the 4th we just saw was 1. 1 times I is I. Okay, my thing just froze. Okay, that just is weird. That just went away. So notice we're going to start over here. So if I did I to the 6th, this should give me back the -1. So I to the 6 is I to the 5th times I, which is equal to I, because I to the 5th is I, times I, which is equal to I squared, which from above is -1. So basically it's repeating itself every 4th power. And so to figure out what this is, there's a rule. So if I was taking I to the 150th power, I would not want to have to go through what I was just doing. And so we can use this rule that says if you have I to the nth, this is the same thing equivalent to what you would have if you looked at I to the rth power, where R is the remainder of n divided by 4. So I to the 150th. So I need to see how many times does 4 go into 150. Well, 4 doesn't go into 1, it goes into 15 3 times. 3 times 4 is 12. 15 minus 12 is 3. 4 goes into 37 times. 4 times 7 is 28. I'm going to have a remainder of 2. So by this theorem, this is the same thing as I to the 2nd power, which is -1. Which if you didn't know, you could deduce it by knowing that I equals square root of -1. So square root of -1 times square root of -1 would be -1. So let's say you had 5 minus 3i that quantity is all times the quantity 2 plus 4i. So it might say perform the following operation and simplify. Or it might say, and put your answer in the form a plus bi. Okay, so we're just going to do this like we would have done this as if we had variables in here. Again, we just need to remember I squared is -1. And so we're going to distribute our 5 to all the terms in the second parentheses. So 5 times 2 gives us 10. 5 times a 4i, well, 5 times 4 is 20. So this is going to give us plus 20i. We're going to distribute the negative 3i to each term in the second parentheses. So negative 3i times 2, this is negative 6i. And negative 3i times positive 4i. Well, negative 3 times positive 4, that's a negative 12, times I squared, which is equivalent to -1. So let's simplify this a little bit. And so we have here 10. Well, we have a positive 20i minus a 6i. So 20 minus 6, so this is plus 14i. And negative 12 minus 1 times -1. So this is positive 12. I can add my real parts, 10 and 12. So 10 plus 12 is 22 plus 14i. Okay, so division is a little different. So division of complex numbers. Let's do this first. Okay, so we're going to let z equal a complex number, let's say a plus bi. The conjugate of this and it's written with z with a horizontal bar over it. This is equal to changing the sign in between your real part and your imaginary part. So this would be equal to a minus bi. So let's look at what happens if we multiply a complex number times its conjugate. So let's find z times the conjugate of z. So we were just saying that z here was equal to a plus bi times the conjugate of z, which is a minus bi. So notice this is actually a difference of squares. And so I can FOIL this out, but our middle term is always going to cancel out if you're multiplying out a difference of squares. So this gives me a times a is a squared. This would give me a negative abi. This is a positive abi, cancels. And then we have a minus, and then we're squaring bi. So bi times bi, this is bi quantity squared. So let me just simplify that a little bit. So this is a squared minus, I'm squaring a term bi. So bi times bi, b times b is b squared. I squared, remember I squared is -1. So if we multiply a complex number to its conjugate, we get a squared plus b squared. Notice that our imaginary part goes away. And so we're going to use this fact when we're dividing complex numbers. So if you're dividing by a complex number, to get rid of the imaginary part in the denominator, we can multiply by the conjugate. So when we're, question? So when we're looking at division, you're going to multiply by a fancy one to get rid of that imaginary number in the denominator, and that fancy one is going to be the conjugate of that denominator. So for example, let's say we had 3 all over 5 minus 7i. And I would say perform the following operations and put this in the form of a plus bi. So we want to use that fact that we just showed. We want to get rid of the conjugate or the imaginary parts. We're going to multiply by the conjugate, 5 plus 7i. So let's distribute this 3 to each term in the numerators over here. So 3 times 5 is 15, 3 times 7i, so that's plus 21i. Using the fact that this is a difference of squares, and so we could just square the 5. I'm just going to keep it as minus. Minus, and I'm going to square my 7i. 15 and 21i are not like terms, so I'm just going to leave it like that in the numerator. So 15 plus 21i all over 5 squared is 25 minus, well, 7i times 7i is 49i squared. So that is actually negative 49 with a negative in front. So this will be plus 49. So we have 15 plus 21i. And if we sum the denominator, 25 plus 49 down here in the denominator, what do we get? We get 74. So if you put this into my math lab and they had told you, or if I told you on an exam to put it in a plus bi form, you're not quite there yet. So they would probably tell you sorry, and then they would spit out, although your answer is correct, it's not in the correct form. And they might clue you into what to do. But all we want to do is be able to rewrite this as the real part plus the imaginary part. And since this is a single term in the denominator, we could just break this down as 2 separate fractions. So this is the same thing as 15 over 74 plus 21 over 74. I could put the I up here in the numerator. It's the same thing as pulling it out right there. Okay. This is the second semester I'm using this textbook, so it's a little different than the one I've been using for 6 years. Or no, not that long, 4 years. They throw in a couple of different things that the other textbook did not. And so I want to make sure I didn't miss anything. So there's a couple of theorems in here that have to do with our value of z and the conjugate. Okay, so there's a couple of theorems. And this states that the conjugate of a real number is a real number itself. Is the real number. Itself. So as you get further in math, you're going to be starting to prove more and more things of why those things are true and why you can use this. Well, let's just look at that. So if we had some complex number, z equals a plus bi, but this is, Z is a real number, where Z is a real number, then I know that if that's the case, then B has to equal 0. So I could rewrite this. Well, actually, I could rewrite the conjugate. Conjugate is A minus BI. And notice that if B has to be 0 in order for this to be a real number, so Z then is equal to A plus zero I, or Z is equal to A. Or in the conjugate, same kind of idea. Conjugate is equal to A minus BI, but we said that B was 0. And so the conjugate here is A. So we just showed that if you started out with a complex number and it was just a real number, then the conjugate would be the exact same number. So there's another theorem that says basically if you take the conjugate of the conjugate, you would get back the original complex number Z. And so we can show that proof. Well, if we let Z equal A plus BI, then we know that the conjugate of Z is equal to A minus BI. But the conjugate of the conjugate, so that's equal to the original A minus and then negative BI. So this is equal to A plus BI, which is equal to Z. So once you finish your proof, and it's kind of satisfying to do this, a lot of mathematicians, or at least this was what they were doing when I was an upper grad in mathematics or grad student, you put a little box at the end. So this just says that you're done proving what you're set out to do. Let me see anything else. Another theorem. This says if you sum two complex numbers and then you take the conjugate of that sum, this would be the same result as if you looked at the conjugate first of Z and then added it to the conjugate of W. Okay, so let's see if we can prove that. And so let's define Z as some complex number and W as another complex number. Just don't want you to get confused by all the bars. Okay, so proof. So let Z here, again, let that be A plus BI. And let's choose W to equal, well, I want different letters. So let's do C plus DI. So the conjugate of Z, we know that is just changing the sign in between. So it's A minus BI. And we know the conjugate then of W is C minus DI. So let's first look at what is So we want to find what the conjugate is after we sum our two complex numbers. And we want to find what the sum would have been if we first took the conjugate of both of the complex numbers and sum them and show that those are the same. So, but what we defined above, we know that z plus w and the conjugate of that. So I could write this as my z value, rewriting what z is a plus bi plus my w, which was c plus di. And I'm going to take the conjugate of that. So remember, the conjugate is the sign, the different sign between the real and the imaginary. So what we want to first do is group our real parts together, and we want to group our imaginary parts together. So we can reorder the way that we're summing this. And so underneath what we're taking the conjugate of. So a plus c would be my real parts. And then plus bi plus di. So we could technically factor an I out of both of those terms, right? And so if I factored an I out of both of those terms, I could write it as plus parentheses b plus d. And I pulled out the I. So to drop that conjugate bar, I would be basically changing the sign in between the real part and the imaginary part. And so my real part staying the same, a plus ci. I'm sorry, a plus c. Jumping ahead. And now this becomes minus, still have the parentheses, b plus d, I. So I can leave it like that, or I can kind of distribute. So maybe I don't know, let's just distribute. So we have a plus c. I'm going to distribute a negative I to both the b plus the d. So negative I times b is negative bi, and negative I times d is negative di. Okay, so this is one side. And we want to show, if we look at z plus, or the conjugate of z plus the conjugate of w. Well, the conjugate of z is just a plus bi plus the conjugate of w, right, is, sorry, not a plus bi, a minus bi. And the conjugate of w, so that's plus, the conjugate of w is c minus di. We really don't need those parentheses. We can group our real parts together. So that would be a plus c. We can group our imaginary parts together. So minus bi minus di. And so notice this is exactly what we have above here. So this is the same thing as z plus w, summing that and then taking the conjugate of the result. Just see if there's any other ones in there. One more theorem. I'm not going to go through proving it. Maybe I'll have you guys do that on Thursday when we come back as an in-class exercise, or it could be a good test question. But the other theorem with these complex numbers says that if you multiply two complex numbers together and then you take the conjugate, it's the same thing as if you first take the conjugate of each complex number and then multiply them together. Again, I just saw this. Okay, so some of this section is solving quadratic equations. And when you're solving the quadratic equations, you're getting negatives under the radical. And so now you wouldn't say there's no real solution. You would actually give what the complex number solution was. So I'm not going to go over any of those. I just wanted to kind of state that. So it looks like we finished and we got through all we needed to in 1.3. So you should be able to add, subtract, multiply, divide complex numbers, take I to some certain power, and then deal with conjugates in these theorems.